In this podcast, we're going to introduce the concept of chirality. And chirality is a complete departure from everything that you've learned thus far. We were trucking along good, everything made sense, it was totally systematic, and it just gets a little weird when we talk about chirality in organic compounds. All right, so chirality is when you have objects that have non-superimposable mirror images. We consider those to be chiral. And I know the term non-superimposable mirror images means absolutely nothing to you. So let's talk about something that is familiar to you. We'll talk about your hands. All right, so you're going to see in this section that we are going to draw a line between two molecules quite frequently, and we consider that to be the mirror. So what we're imagining is if we put our left hand up to the mirror, we would expect to get a mirror image where the pinky of your left hand is closest to the mirror. Okay, so we would expect our pinkies to be closest and our thumbs to be furthest away. All right, so that's what it means to have a mirror image. Okay, so if I were to hold this up, this would be the mirror image. This would be the mirror image of this hand. What it means to be non-superimposable means that you can't lay those two objects on top of each other and have them be facing the same direction and lay in an imposable way. So follow me for a second. So these are mirror images. My thumbs are closest, my pinkies are furthest, palms are facing forward. This is a mirror image of itself. My left hand is a mirror image of my right hand. They are not superimposable, meaning I can't keep my palms towards you and lay these on top of each other and have my thumbs line up with my thumbs and my pinkies line up with my pinkies. Okay? I know what you're saying. Yes, you can. I can get them to line up, can't I? But notice that it's not palms forward on both hands. Okay? In order for these to be facing the exact same direction and be superimposable, both my palms have to be facing you, and I can't do that. The only way I can make them superimposable is to turn one so it's upside down. Upside down. Okay? So they're actually not superimposable. Yes, they're mirror images of each other, but no, you cannot superimpose them and have them facing the same direction and have all the fingers line up correctly. All right, so if something is chiral because it has mirror images that are not superimposable, something is achiral if it can be superimposed on its mirror image. And I think socks are a really good example of this, or at least I thought they're a really good example. So your typical sock, it doesn't matter which sock goes on the left foot or the right foot. They're tube socks. So here we can see this is our mirror. And the heels are closest and the toes are furthest away from each other. So this is the mirror image. However, if I were to take two socks and lay them on top of each other, I would be able to make them superimposable. They are achiral because the mirror images can be laid on top of each other perfectly. They can both be facing the same direction. All right, new term for us. Enantiomers are mirror images of each other that cannot be superimposed. So if something has chirality, it would be considered an enantiomer. These are typically asymmetrical. Okay, we'll talk more about what that means. If this sounds like someone is doing drugs and talking chemistry to you, that's exactly what it should sound like the first time that you experience this. But just hang with me. We're going to get some practice on chiral versus achiral. All right, let's practice. So in A, we have two nails, okay? I don't like the way they set this up, but if we were to do a mirror image, they would look something like that. Okay, those are the mirror images. If you were to lay two nails on top of each other, you could have the heads pointing the same way and the pointy end pointing the other way. They would be superimposable. They're symmetrical. They are superimposable, so we would consider nails to be achiral. Screws are a little different. You may have heard that screws either have a left hand screw or a right hand screw. They can go in two different directions. Because of this, If you were to put the mirror image of a screw next to itself, because there's direction to the way the screw spirals, oh good Lord, I'm leaving it in, guys. There's direction to that. Those two mirror images are not superimposable. So we would consider screws to be chiral, to have chirality. You cannot superimpose those mirror images. All right, back to the hands. Hands are always such a good example of chirality, but here we have a glove with a thumb. It's not like one of those gloves that doesn't fit your hand very well. If we were to do a mirror image of our glove, we would have mirror images. Pinkies closest to each other, thumbs furthest away. But again, these are not superimposable. Okay, you can't have the backs of your hands facing the same direction and superimpose it. It would take changing directions for that to happen. So because the mirror images are not superimposable, we would consider this also to be chiral. All right, a pencil, if we were to put a mirror here and draw the mirror image of the pencil, those have symmetry to them. You would be able to take two pencils and lay them on top of each other, and they would be superimposable. You can face them in the same direction and have them lay on top of each other even though they are the mirror image of one another. So we would classify this as being achiral because the mirror image is superimposable. That's fine and all, but let's get to the chemistry of it. So if we had two molecules like water, we can put them up against that mirror and we can see the mirror image. So you can see that water has a mirror image. If I were to try to superimpose two water molecules, they would be superimposable. I can lay these on the top and have my bonds pointing the same direction, as you can see with these two water molecules. So here we have the mirror image, okay? I can lay them on top of each other. I can superimpose them, okay? The bonds are pointing the same direction, okay? I don't have to turn them upwards. They are superimposable. So this water molecule is considered to be achiral because of that. All right, so where this gets a little tricky is with a little more complex molecules. So here we have a carbon that has three different types of atoms on it, two hydrogens, one halogen, and an oxygen. So as you can see, the green molecule, the green bubble, is closest to each other. The red is coming out towards you. Okay, we have a white pointing up, and we have a white pointing out to the sides. Okay. So these are mirror images of each other, okay? So these are mirror images. If I were to try and superimpose these, where I have all atoms facing the same directions, I should be able to do that. Right there, there it is. Okay, my greens are facing the same direction, my reds are facing the same direction. I have two whites pointing up and two whites coming out at you. Okay, so those are considered, oh, it's tough to see with my big old hands. Those are considered superimposable. That's tough. Build two of these with your model kit and give it a try. Okay, so this is considered achiral, but watch what happens if we replace one of the hydrogens on each molecule with whatever the yellow is. Let's call it sulfur. Okay, so again, we're going to go ahead and we're going to point everything in the same direction. So my yellows are closest together. Okay, this time I have silver coming out at you. I've got green pointing back and I've got white pointing up. So these are mirror images of each other. Okay, now when we try to superimpose these, let's start with the yellow. Let's try to get the yellow lined up. Okay, so yellow is facing the same direction, but notice that now we have green going the same direction. We have our whites going in the same direction, but the green and the silver don't match up. Okay, I could solve that if I were to turn this molecule like this. So now notice the silvers are coming out towards you, green is up, okay, yellow is back, but the hydrogens are not going in the same direction. The hydrogens are pointing in opposite directions to each other. Because there's no way I could turn these and get them to lie perfectly superimposed. Remember the palms have to be facing the same way, so every atom has to be facing the same direction. This is considered a chiral molecule. Again, build 2 of these, give it a try on your own. All right, so the reason I like to take out the molecule or the model kit is because I think it's misleading on paper. When we draw this in a 3D plane, or a 2D plane, excuse me, we can put the chlorines closest together, the bromines furthest away, iodines down, hydrogens up. It looks like I could take these 2 molecules and superimpose them. But it's when you put them into the 3D, we have 4 different molecules around a central carbon, you find that you cannot turn everything into the same direction. You cannot point everything in the same direction and still superimpose it. It just does not work. So I encourage you to get your model kits out. So let's define what we just worked through with our models. How do we identify chirality? In a molecule, you have a compound that's chiral if it has at least 1 carbon bonded to 4 different atoms or molecules. Okay? When we looked at this molecule, we knew that the carbon was achiral because it had 2 of the same atoms bonded to it. But we knew that this guy was considered chiral because he had 1, 2, 3, 4 different atoms bonded to a center carbon. A compound is achiral if the carbon is attached to 2 identical groups. That means it can be turned in a way where it can be superimposed. Your mirror images can be superimposed. That means it's achiral. If you have any double bonds present, automatically you can't have 4 different groups. Automatically there's no chiral center. The molecule is achiral. So let's look at our 2 examples here. Here's our center carbon. Okay, let's look at our groups. We have a methyl group, a hydroxyl group, a hydrogen group. So far we have 3 different groups, but we have another methyl group. Because these are 2 of the same groups, there are only 3 different groups, we consider this molecule to be achiral. Looking at our second example, we have a carbon with an ethyl group on it, a hydroxyl group, a methyl group, and a hydrogen group. This has 4 different groups around a center carbon. Therefore, this is considered chiral. All right, compounds can have more than 1 chiral carbon in them. So let's look at this example on the bottom. If we were to look at this carbon, it is attached to 3 hydrogens and 1 other carbon. Okay, this carbon's attached to 2 hydrogens and 1 other carbon. So notice that you have doubles of groups. There's identical groups there, and usually it's hydrogen. None of those are considered to be chiral. But when we move into the center one, let's take a look at this. So we have an OH group, a CH3, an H, and 1, 2, 3, a propyl group. Those are 4 unique different groups from each other. So we would consider this molecule to have 1 chiral center. We didn't even look at this methyl group because it's a carbon with 3 hydrogens on it. Wouldn't count. All right, looking at our other example, okay, when you see COOH written like this, what this really means is that you have a carboxyl group, okay? COOH is just an easier way to write that. So we wouldn't look at this carbon because there's a double bond, automatically achiral. So let's go down to the next carbon that we have. This carbon has an amine, a hydrogen, a carboxyl group. Those are 3 different groups. Now watch what I do. Okay, this entire section is considered its own unique group. So this carbon in the center has a hydrogen, an amine, a carboxyl group, and then everything down below. Looking at our next carbon, Okay, it is attached to a hydrogen, a methyl group, an ethyl group, and then look at this. We look at the entire top portion as being a separate group. So that is 4 separate groups. So we have 2 carbons that are each showing chirality. So we would say that this has 2 chiral centers. All right, so chirality is everywhere. I know what you're saying. You're like, God, this is like the most unique thing. I'm never going to use this again. You're using it and you don't even know it. Snails use it. So a lot of snails are going to have a chiral right-handed shell. So if you were to look at snails, you'd notice that they open and spiral down to the right. Well, that has chirality. If you were to put a right-handed snail up against a mirror, okay, it would have a mirror image, but it would be non-superimposable. So it's an enantiomer of itself. This is not that big of a deal if you have a bunch of right-handed snails. It becomes an issue if you have a snail that has a genetic mutation causing it to have a left-handed spiraling shell. If a snail were to spiral in the wrong direction, that left-handed spiraling snail cannot get in the right position with the right-handed spiraling snail to reproduce. So this mutation becomes a form of mechanical isolation. It's a reproductive barrier for this poor left-handed snail. So there was a little while back where a left-handed snail was found and they couldn't find it a mate. So there was a worldwide search for, his name was Jeremy, the lonely left-handed snail. And there was a search to find him another left-handed snail so that they could mate. That is another story for another day to go into that. I'm not even going to tell you if it was successful or not. Look it up. Pretty interesting story. Honeysuckle is another example. Honeysuckle will wind in a chiral left-handed helix as well. So we do see a lot of this in nature.